Hey everybody, thanks for tuning in. So this is going to be part 4 of our video lecture series on stellar evolution. And in this video, we're going to be discussing the last evolutionary stages of a low-mass star. So let's just jump right in. So in the last video lecture, we discussed how a sun-like star would evolve out of the main sequence. And we pretty much left off in the supergiant phase. And in the supergiant phase, that's where you have carbon just sitting at the core because it was a byproduct of helium fusing into carbon. And the layers just outside of the core are going to be the ones fusing hydrogen and helium. So here's the thing though. For these low-mass stars, in order to start fusing carbon, they need to be massive enough. However, because of their low mass, they actually can't start fusing carbon. So it just starts to sit there. Meanwhile, you have the layers just outside of the core still continuously producing energy, which means it's going to throw this whole star out of equilibrium, causing the core to shrink while causing the outer layers to actually start expanding and causing the star to get bloated. And so what this results in is that as a star gets larger in size, then the outer layers will feel the weakest gravity. And so therefore, the star literally starts to shed its outermost layers. And this basically leads to the star losing a lot of mass in a very short amount of time. And so when the star is doing this, then there's a chance that you might be able to view this as a planetary nebula. So just to clarify here, the name planetary nebula is a little bit misleading, but it has actually nothing to do with planets. And we still use that term because of historical reasons. When astronomers first discovered planetary nebula, they thought it was actually a crucial stage in planetary formation. However, now we know that these objects typically form after a supergiant has shed most of its atmosphere. And so this is a pretty short-lived phase. On average, they last about 50,000 years. And so what I want to talk about now is why we're seeing what we're seeing here. So in this planetary nebula that's pictured here on the left, you can see there is a gradient of colors where you see a red envelope that surrounds this like blue bubble, and also on top of that, if you look at the very middle, there's going to be this tiny white dot. And so we'll talk about like a basic mechanism of how that's actually formed. So when the supergiant star starts to shed its outermost layers, well, it's going to start off with the coldest layers first. So if that is cold, then that means that they're going to be moving slow as they get dissipated in all different directions. However, as the layers start to unravel, layer after layer, now you're exposing the hotter regions of that supergiant. And when they get dissipated, because they're of higher temperature, they're going to be moving faster on average. Eventually, they're going to catch up with the colder exterior layer. And so effectively what's going to happen here is that the hotter inner layers will heat up the slower outer layers that was dissipated, causing them to glow because you're essentially exciting those atoms in the colder outer layers, and you'll be able to observe that light coming from them. And that's what's actually being shown here in these two diagrams. The diagram on the left shows first a slow-moving wind coming from the outermost layers of that supergiant star, and then the right diagram shows you the inner layers getting exposed, and they're hotter, and they're actually catching up with those outer, colder layers. And so in the Helix Nebula, you can see here how now that works. And what we just talked about there, I do want to point out that that was basically like the simplest way you can make a planetary nebula. However, from what we've seen, it's actually more normal to see complex looking nebula. So for example, if you look at the Cat's Eye Nebula here on the right, it looks vastly different from the Helix Nebula. And in fact, I actually can show you more nebula here, and you can see how they all look different from each other. Now, there are some common features here. So, for example, you can see that the nebula here, they have some sort of outflows going in opposite directions. So, if you look at the butterfly, the twin jet, and the egg nebula, you can see that there's basically like these jet-like features that are going in opposite directions. And what we think, and again, this is still an active field of research, the reason why nebula can look more complex is because around a star, you can have other objects around that star, and as the star is shedding its outermost layers, then those objects can also disturb that and cause the nebula to have a more deformed formation. So what I'm going to do here is I'm going to show you some of the videos or animations here that people have done before to kind of figure out how you can form different types of nebula. So here's the first one, where this is like your basic nebula. You have a simulation, and it's going to compare it to what's actually being observed. So let me just play that. So first it starts off red, and again you're showing the outermost layers, and then it starts increasingly becoming less red towards shorter wavelengths, so it tends to get bluer. And then now you have the hotter inner layers catching up with the colder outer layers, causing that blue light that you're observing towards the middle. And you can also see the white dot that I'm talking about, because that's essentially the core now being exposed. And we'll talk about that in a second. And so compared to the image you actually observe using the Hubble Space Telescope, so it's a pretty close match here, as you'll see as you zoom out in this video. Okay, and again, this was a simulation, assuming some basic physics that was happening. And when you have your simulations matching your observations, again, that gives us more confidence that however we're explaining why and how this happens is actually true or correct. So here's another one. And in this video, it's going to show you that the supergiant star actually has a companion, or a binary star. So as these two stars are orbiting each other, they're going to get closer and closer, and eventually, if the supergiant gets close enough, then the outer layers that are closest to its companion star will get pulled in by that companion star's gravity, and then because they're orbiting along some sort of plane, that's going to cause the planetary's nebula's axis to be biased off one direction, causing these outflows to go in opposite directions. Okay, so let's go back to my slides here. All right, sorry about the wait on that. Okay, so now let's talk about that white dot in the middle, because that's essentially the core of that supergiant star, and you'll be able to see that once all of the outer layers of that supergiant star has been expelled in all different directions. And remember, we basically had a core that's composed mostly of carbon. And that carbon core is what we actually call the white dwarf. And so these white dwarfs, because they're so dense, they're essentially held up by electrons pushing against each other. And those electrons are kind of just fixed in place. And remember, we had a special name for that. That's called electron degenerate matter. And so these stars, or these white dwarfs, are no longer fusing, and so whatever light you're observing from them, it's basically residual heat. And what's eventually going to happen is that these stars will cool down, they're going to harden, they're going to crystallize, and essentially redden over time. In fact, some astronomers actually believe that the carbon center may even form diamonds. When it comes to the size of these white dwarfs, they're extremely tiny because they're basically the same or comparable size as the Earth, shown here on the figure. Um, and then they're extremely dense because they're basically Earth-sized, but then they can have a mass that's comparable to our own sun. So if you were to shrink down our sun to the size of the Earth, that is a whole lot of gravity if you were able to stand on the surface of a white dwarf. And I believe we talked about that before in the HR diagram video lecture, where I said if you can take a teaspoon of a white dwarf, that's going to be about 10,000 tons. So essentially, you would be crushed if you were able to stand on the surface of a white dwarf. All right, so this is pretty much it for how low mass stars evolve. And in the next video, we're going to be discussing how high mass stars evolve out of the main sequence and their last steps in their evolution. Okay? See you guys next time.